that little cardboard blister pack sitting in your medicine cabinet right now. You know the one, the famous Z-Pak?
Oh, absolutely.
If you've ever had a really stubborn, chest-rattling respiratory infection, there is a very high chance your doctor has handed you one of those.
Yeah, it's incredibly common.
You pop those pills for just a few days, and suddenly, I mean, you can breathe again. It feels like the absolute pinnacle of modern engineered medical precision.
Right. It feels very high-tech.
But the wild truth is the origins of that highly convenient, ubiquitous household staple, it can be traced directly back to a single scoop of dirt collected in the Philippines in 1949.
It sounds like a myth, honestly.
It really does.
But it is entirely factual. And to truly grasp what these drugs are doing, we have to look past the convenience of the blister pack. We have to understand not just what they're meant to kill, but how they negotiate with human biology on a molecular level.
Okay, let's unpack this. Today's deep dive is venturing into a stack of pharmacological sources all about a massive family of drugs called macrolides, specifically focusing on azithromycin and its siblings.
Which is a fascinating family of drugs.
It is. We are looking at the mechanics of how these drugs actually work, their incredible real-world applications, and, the hidden, sometimes severe risks that come with their sheer convenience.
Well, to really appreciate the problem that a drug like the Z-Pak solves, we actually need to look at the medical landscape of the early 1950s.
Okay, set the scene for us.
Coming out of World War II, penicillin had been hailed as the ultimate global miracle drug. I mean, it saved countless lives.
Right, the golden age of antibiotics.
Exactly. But by the time the 1950s rolled around, that miracle was already showing severe, terrifying cracks.
Because the bacteria were mutating and fighting back against the penicillin.
Very quickly, yes. Staphylococcus aureus, which is a major culprit in hospital infections, had developed a brilliant defense mechanism.
What did it do?
It started producing an enzyme called penicillinase. And this enzyme would literally seek out the penicillin molecule and break it apart before the drug could do any damage.
Oh, wow. So it just disarmed it completely.
Completely. And alongside this bacterial resistance, doctors were seeing a rapid rise in severe, life-threatening allergic reactions to penicillin in the general population.
That sounds like a nightmare scenario.
The medical community was terrified. Their primary weapon was failing, and they desperately needed a structurally entirely different kind of weapon.
So they needed a backup. But how do we get from a post-war medical crisis to, a scoop of dirt in the Philippines?
That is where a physician named Abelardo Aguilar comes into the picture.
Okay.
He was working for the pharmaceutical company Eli Lilly, and he was stationed out in the Philippines in 1949. As part of a massive effort to find new compounds in nature, he collected a soil sample and just mailed it halfway across the world to a researcher named J.M. McGuire at a lab in Indiana.
Wait, just literally mailing mud across the globe, hoping there's something useful inside it?
Yeah, that was standard natural product discovery at the time.
That is wild.
It was. And McGuire's team cultured the microorganisms living in that dirt. They managed to isolate a specific soil bacterium, eventually classified as Saccharopilospora erythraea.
That is quite the name.
It is. And from that single organism, they extracted a chemical compound that possessed an incredible ability to stop bacterial growth dead in its tracks.
No kidding.
Yeah, they patented it, and by 1952, it was on the U.S. market under the name aliticin. This is erythromycin, the very first macrolide antibiotic.
It makes me think of an army on a medieval battlefield.
Okay, how so?
Well, your front lines have been using a specific type of armor, maybe chainmail, which is your penicillin. But the enemy figures out how to forge specific arrows that pierce the chainmail perfectly.
Right, that's the penicillinase enzyme.
Exactly. You can't just make the chainmail thicker. I mean, you need to invent solid plate armor. You need a completely different defense that their weapons simply aren't designed to penetrate.
That's a great way to think about it.
But if erythromycin isn't attacking the bacterial cell wall the way penicillin does, what is its actual target?
It goes after the bacterial ribosome.
Oh, yeah.
And if you think back to basic biology, ribosomes are essentially the protein factories of any living cell.
They're the machines that read the genetic code and physically build the proteins that the cell needs to function, right?
That is the perfect way to look at it. Now, bacterial ribosomes are constructed from two main pieces, known as the 30S and 50S subunits.
Okay, 30S and 50S.
Right. The macrolide drugs completely ignore the 30S part. They zero in and bind specifically to the larger 50S subunit.
Just that one specific piece.
Yes. And they don't just attach randomly. They lodge themselves physically inside a very specific channel called the nascent peptide exit tunnel.
The nascent peptide exit tunnel.
Yeah.
So if this is a factory, that tunnel is the literal chute where the newly manufactured protein chain is supposed to slide out into the cell.
Exactly. The ribosome builds the protein chain and pushes it down that tunnel. But when a macrolide is present, it sits right inside that exit chute.
I picture that like taking a wooden wedge and just forcefully shoving it straight into the output nozzle of a 3D printer.
Oh, yes.
Like the machine still has electricity, it still has the digital instructions telling it what to build, but it stalls completely.
Right, it jams.
The plastic has nowhere to go, nothing functional can come out.
A fantastic visualization. Because that tunnel is blocked, the growing protein chain has no room to advance. It either stalls the entire ribosome complex outright, or the pressure forces the incomplete protein chain to snap off and drop away prematurely.
Either way, it's broken.
Either way, the bacterium is no longer producing the critical proteins it needs. Its growth just stops.
I have to ask the obvious question, though. If I swallow this pill and it acts as a wedge that jams up ribosomes, well, why doesn't it jam up the ribosomes inside my own body? Why doesn't the 3D printer in my cells break down?
This relies on a beautiful structural difference between human cells and bacterial cells. Human ribosomes are physically distinct. Yes, our machinery is built from different subunits, specifically 40S and 60S pieces.
Ah, so not the 30 and 50.
Exactly. Because the physical architecture of a human ribosome is slightly different from a bacterial one, the drug's physical shape simply does not fit into our exit tunnels.
So it just bounces off.
It's like trying to use a key in the wrong lock.
Yeah.
It ignores our cellular machinery entirely, which provides a massive safety margin for you when taking the drug.
Okay, here's where it gets really interesting. Our sources point out that azithromycin, the star of the Z-Pak, isn't actually a true macrolide by strict chemical definitions?
Well, it is a bit of a debate among chemical purists.
How so?
A classic textbook macrolide is defined by having a large macrocyclic lactone ring at its core. Essentially a big circle of carbon atoms, usually 14 to 16 of them.
Okay, a ring of carbon.
Right. Erythromycin, our Philippine dirt discovery, has that classic 14-member ring. But azithromycin is technically classified as an azolide.
An azolide. So what makes an azolide different from the original drug?
It comes down to a brilliant piece of pharmaceutical tinkering by two chemists in Yugoslavia in 1980.
Okay.
Slobodan Okic and Gabriela Cobrahil were working for a company called Pliva. They took that classic ring structure of erythromycin, broke it open, and inserted a single nitrogen atom into the ring, expanding it to 15 members.
Wait, they just spliced one nitrogen atom into the circle?
Just one.
If erythromycin was already saving lives, why mess with the underlying chemistry?
Because erythromycin came with a massive, incredibly painful flaw. It is highly acid labile,
Meaning it hates acid.
meaning it breaks down very easily in acidic environments. When a patient swallowed a pill, the harsh acid in their stomach would destroy a huge fraction of the dose before it could even reach the intestines to be absorbed.
Oh, so you're losing the drug before it even does anything.
Right, but the bigger issue was that the degraded byproducts of the drug severely irritated the gut lining.
Oh, no.
It caused intense nausea, cramping, and severe diarrhea. For a lot of people, the stomach pain was so agonizing, they preferred the infection over the cure.
So the addition of that one nitrogen atom, did that act like a shield against the stomach acid?
Precisely. Inserting that nitrogen atom created the azolide structure, and it made the entire molecule acid stable.
Wow.
Suddenly, the drug could survive the journey through the stomach without breaking down into those toxic, irritating byproducts. It solved the nausea problem and allowed the body to absorb a much larger percentage of the active drug.
That is brilliant.
Pfizer eventually saw the potential, licensed the compound, and introduced it to the U.S. market in 1991 under the brand name Azithromycin.
It's crazy that moving just one atom around completely transformed the human experience of taking the medication.
It really is.
But the sources highlight that the single nitrogen atom didn't just soothe stomach aches, it completely rewired how the drug moves through the body, right?
It radically altered its pharmacokinetics. That nitrogen atom changed the drug's solubility and how it interacts with cellular membranes.
Okay, what does that mean in practice?
Well, instead of just floating in the blood, azithromycin does something highly unusual. It aggressively accumulates inside your own tissue cells, particularly in fibroblasts, which are the cells that build the structural framework of your tissues, and in phagocytes, like your macrophages.
Wait, macrophages are the white blood cells that act like the immune system's garbage disposals, right?
Yes, exactly.
They wander around eating cellular debris and invading bacteria. Why does the drug end up in there?
Because of that nitrogen atom, the drug molecule becomes slightly basic. Macrophages have highly acidic compartments inside them used for digesting the bacteria they eat.
Ooh, I see where this is going.
When the azithromycin molecule drifts into that acidic compartment, it picks up a proton, gets an electrical charge, and suddenly it's trapped.
It can't get out.
It can't cross back out through the cell membrane. This is called ion trapping. The drug concentrates inside these immune cells at levels sometimes 50 times higher than what is floating in your bloodstream.
That is wild. The immune system cells inadvertently swallow the drug and act as Trojan horses, carrying the antibiotic right to the site of the infection.
That is exactly what happens.
Yeah.
Because it gets locked deep inside your tissues, your body takes an incredibly long time to process and excrete it. We measure this persistence using a half-life.
Right.
The original drug, erythromycin, has a half-life of roughly 1.5 hours.
Okay.
Azithromycin's half-life is staggering. It's widely cited at around 68 hours.
68 hours. Okay, for you listening, this explains everything about the Z-Pak experience.
Well,
this is the exact reason your doctor only prescribes a 3 to 5 day course.
Precisely.
You finish the last pill in the blister pack by Thursday, but because of that massive 68-hour half-life, the drug is still heavily concentrated in your tissues. It's actively jamming up bacterial 3D printers through the entire weekend and well into the next week.
Yes.
You stop taking the pills, but the therapy continues on its own.
And that deep tissue penetration, coupled with the incredibly long half-life, unlocks one of the most stunning public health applications in modern medicine.
What's fascinating here is how they use it for things other than just a bad cough.
Right. We have to look at how this drug is used to fight trachoma.
I saw trachoma mentioned in the stack. What exactly is that?
It is a devastating eye infection caused by the bacterium Chlamydia trachomatis. It is endemic in many rural, resource-limited communities across Africa, parts of Asia, and Latin America.
What does it do to the eye?
When someone is repeatedly infected, the chronic inflammation causes the inside of their eyelid to form scar tissue.
Oh, that sounds awful.
It gets worse. That scar tissue eventually contracts and forces the eyelid to turn inward, meaning their own eyelashes constantly scrape against the surface of the eyeball.
Oh my God.
It is agonizing, and it is the world's leading infectious cause of blindness.
That sounds like an absolute nightmare. How does a drug like azithromycin help if they are in remote areas without easy access to hospitals?
The World Health Organization developed a multi-pronged approach called the SAFE strategy. Surgery, antibiotics, facial cleanliness, and environmental improvement.
Okay.
The antibiotics pillar relies almost entirely on azithromycin. Because of that 68-hour half-life where the drug stays locked in the tissue, doctors don't need to prescribe a complicated 10-day course of pills that had to be taken with meals. They can achieve a cure with a single large oral dose.
Just one dose.
One dose. And that logistical simplicity allows public health workers to conduct mass drug administrations.
Oh, I see.
They can travel to a remote village where follow-up care might be impossible and simply administer that single dose of azithromycin to every single person in the village all at once, usually on an annual basis.
That is staggering. It stops being individualized medicine and becomes sheer public health infrastructure.
Exactly.
You hand out one pill to everyone and drastically reduce the rates of infectious blindness across an entire population.
It truly is a logistical triumph. But the reality of pharmacology is that every advantage comes with a cost. The very trait that makes azithromycin a global miracle.
The long half-life.
Yes, its lingering 68-hour presence in human tissue is the exact mechanism that is driving a massive crisis today.
Because it's a double-edged sword. As that drug lingers in your tissue for days and days after the pills are gone, the concentration of the drug is slowly, inevitably dropping.
Correct. Eventually, the concentration falls to a sub-therapeutic level. The wedge is no longer wedged tight enough.
So it's not fully jamming the printer anymore.
Right. It isn't strong enough to stall the bacteria completely, but the drug is still hovering around in the environment.
So it's basically giving any surviving bacteria a prolonged, low-stakes training ground. The bacteria get to interact with a weakened version of the drug for days, giving them all the time in the world to mutate and figure out how to defeat it.
It is the textbook recipe for selecting resistant mutants. And the bacteria have evolved two incredibly sophisticated ways to fight back against these drugs.
Okay, let's hear them.
The first mechanism involves what geneticists call ERM genes, ERM. These genes give the bacteria the ability to methylate their own ribosomal target site.
Methylate. Let's break that down. Keeping with our 3D printer analogy, if the drug is a wedge designed to fit perfectly into a specific slot in the printer, what does methylation do?
Methylation means the bacteria chemically attaches a bulky molecular group onto that slot. It physically changes the shape of the lock.
It's like the bacteria smears a thick layer of concrete over the slot. The wedge tries to slide in, but the shape is wrong now, so it just bounces off.
That is a perfect way to visualize it. And the terrifying part of this gene mutation is that it grants the bacteria cross-resistance.
Meaning?
Because it changes the shape of the target site entirely. It doesn't just block macrolides, it also blocks entirely different families of antibiotics that happen to target that same general area.
Wow, so the bacteria solves one problem and accidentally makes itself immune to several different weapons at once.
Precisely.
Okay, so they changed the lock. What is the second resistance method our sources mentioned?
The second method relies on meth and Meunier genes. These genes provide instructions for the bacteria to build efflux pumps.
Efflux pumps. I imagine these like tiny, aggressive cellular bouncers.
That's a good image.
Like, the drug molecule manages to penetrate the bacterial cell membrane, but before it can navigate over to the ribosome to jam it up, these pumps grab the drug and physically launch it back out into the surrounding environment.
Exactly. They constantly bail water out of the sinking ship faster than it can flood in. And these two mechanisms, altering the target site and pumping the drug out, they have been devastatingly effective in the real world.
Just how bad is it?
Well, in some regions, resistance to macrolides and Streptococcus pyogenes, which is the bacteria responsible for strep throat, has climbed to 30 or even 40%.
40%. So nearly half the time, the drug simply won't work.
Yes, which is why many updated medical guidelines no longer consider macrolides a reliable first-line treatment for standard strep throat, despite it being the default alternative to penicillin for decades.
I have to jump in here and push back on a massive misconception that drives me absolutely crazy. And, it directly feeds into this resistance problem.
Go for it.
I hear people all the time saying, oh, I have a cold, a bit of a cough. I'm going to ask my doctor for a Z-Pak just in case it gets worse. I want to be crystal clear for you listening. Colds are viral. The vast majority of upper respiratory infections are viruses. Macrolides do absolutely nothing to viruses.
Absolutely nothing.
A virus doesn't even have the cellular ribosome that this drug targets. It's like trying to put out a fire by throwing a wrench at it.
It is a critical distinction to make. Taking a Z-Pak for a viral cold is not a harmless, just-in-case safety net.
Thank you.
Reflexive, inappropriate prescribing for viral infections is one of the primary drivers of this exact resistance crisis. When you take the drug for a virus, you are exposing all the natural, harmless bacteria in your body to the antibiotic for no reason.
You're just training them.
You are forcing them into that prolonged training ground, teaching them how to resist the drug for the day they actually mutate and turn pathogenic.
It's infuriating because it feels like we're squandering the magic. But speaking of how these drugs hold bacteria back, I noticed a debate in the sources about the drug's fundamental strength.
Okay.
We talked about how macrolides are bacteriostatic, meaning they merely stall the bacteria from growing rather than bactericidal, which would mean they explode or kill the bacteria outright. Does that make these drugs inherently weak?
Not at all. That is a very common misunderstanding of how the body handles disease. A bacteriostatic drug doesn't need to kill the bacteria outright to save your life.
Because the immune system is still there?
Exactly. By jamming those ribosomes and halting bacterial replication, the drug simply freezes the enemy lines in place. The infection stops multiplying.
Right.
That gives your own immune system the crucial time it needs to deploy its own forces, sweep in, and actually destroy the invaders.
That makes total sense.
Unless a patient has a severely compromised immune system, or they're dealing with a deeply entrenched infection like endocarditis where the immune system can't easily reach, stalling the bacteria is more than enough for a full recovery.
I see the connection. The drug just buys the immune system time. But as the sources outline, overusing these drugs doesn't just breed resistance. It also exposes patients to hidden risks that we're only just now fully understanding, decades after the drug was approved.
This is a vital point, and it brings us to a major pharmacological wake-up call from 2012.
What happened in 2012?
The New England Journal of Medicine published a landmark observational study led by a researcher named Wayne Ray. His team analyzed massive amounts of historical data from the Tennessee Medicaid system.
Okay, so huge data pool.
Yes. They were comparing patients who were prescribed a standard 5-day Z-Pak against patients taking amoxicillin and against patients taking no antibiotic at all.
And what did they find hiding in all that historical data?
They found a small but statistically significant increase in cardiovascular death for the group taking azithromycin.
Wait, really?
Yes. Specifically, the drug was linked to a phenomenon called QT interval prolongation.
Okay, what does that actually mean for the heart?
Think of your heartbeat as an electrical cycle. The heart muscle fires to pump the blood, but then it has to electrically reset itself before it can fire the next beat.
Right.
The time it takes to reset is measured on an EKG as the QT interval. Azithromycin can stretch out that reset time.
And if it stretches it too much?
If it stretches it out too much, the heart's electrical system gets confused. The next beat tries to fire before the reset is finished, triggering a chaotic, highly dangerous flutter called torsades de pointe.
So a standard blister pack could potentially trigger heart failure.
It is essential to contextualize the risk here. The absolute risk increase was very small. They estimated it at about 47 additional cardiovascular deaths per 1 million courses of the drug in the general population.
Okay, so very rare.
However, that risk spiked significantly in patients who already had elevated baseline cardiovascular issues, like an existing irregular heartbeat or low blood potassium. It was clinically significant enough that the FDA issued a formal safety warning regarding the drug in 2013.
It really proves that even an old, supposedly perfectly understood generic drug can have massive hidden variables that only reveal themselves when you look at millions of data points over decades.
Absolutely. It underscores why physicians have to meticulously manage drug interactions. Interestingly, even with the heart risk, azithromycin is actually far safer than its older siblings, erythromycin and clarithromycin, when it comes to the liver.
How so?
Those older macrolides strongly inhibit a critical liver enzyme known as CYP3A4.
And that enzyme is basically the liver's disposal system for breaking down a lot of other daily medications, right? Like statins for cholesterol or certain blood thinners.
Right, so if a patient takes clarithromycin, it blocks that disposal enzyme. Their statins or blood thinners aren't being broken down and cleared out, so those medications dangerously spike to toxic levels in the bloodstream.
Which is incredibly dangerous.
Exactly. Because of azithromycin's altered azolide structure, it barely interacts with that liver enzyme at all.
Which explains why it became the default choice for so many doctors. It played much nicer with a patient's other medications.
Yes, exactly.
But even with that relatively safer profile, the hype around azithromycin can get wildly out of hand. The sources dedicate a lot of space to a very public, very recent failure, the COVID-19 pandemic.
A fascinating and sobering case study. In early 2020, amidst global panic, a small, heavily criticized observational study out of France, led by Didier Raoult, proposed pairing azithromycin with hydroxychloroquine as a potent treatment for COVID-19.
And the media momentum just exploded overnight. It became a massive talking point globally. Now, looking strictly at the pharmacological data and the clinical trials that followed, what actually happened there?
Looking strictly at the data, the sheer momentum of fear and hope vastly outpaced the scientific method. Subsequent, massively scaled, randomized controlled trials, most notably the recovery trial in the UK, which looked at thousands of patients, proved conclusively that there was absolutely no mortality or clinical benefit from giving azithromycin to hospitalized COVID-19 patients.
None at all.
None. It serves as a stark historical lesson in how dangerous it is when a poorly powered hypothesis gets amplified into standard practice before rigorous clinical trials can test if it actually works.
It caused people to hoard and misuse an antibacterial drug for a respiratory virus, which feeds right back into the resistance problem we just talked about.
It really was a perfect storm.
But before we wrap this up, there is one final, completely bizarre twist from our sources that I have to bring up. We've talked this whole time about how these drugs stall bacteria or fail to kill viruses. But today, the original drug, erythromycin, is often prescribed off-label for a purpose that has absolutely nothing to do with fighting an infection.
This is undoubtedly one of my favorite quirks in all of pharmacology.
It turns out the erythromycin molecule happens to perfectly mimic a natural hormone in the human body, allowing it to bind to and activate the motilin receptor in the human gut.
Yes.
This is the receptor that triggers the housekeeping muscle contractions that squeeze your digestive tract, sweeping food and acid through the system between meals.
Exactly. Because of that side effect, gastroenterologists will frequently prescribe very low sub-antibacterial doses of erythromycin for patients suffering from conditions like gastroparesis, where the stomach muscles are paralyzed and empty too slowly.
They are prescribing an antibiotic purely as a gut motility drug. It perfectly illustrates how a chemical molecule doesn't inherently know what its job is. Its identity in medicine is entirely dependent on what specific accidental effect a doctor is trying to harness on any given day.
The pharmaceutical compound is just a tool. The context of how we deploy it entirely defines its value.
So, what does this all mean? We've covered a massive amount of ground today. We started with a handful of dirt from the Philippines that gave us erythromycin.
We did.
We explored how these drugs act like a wedge, jamming up the 3D printers of the bacterial ribosome. We saw how splicing a single nitrogen atom into the ring created the 68-hour superpower of the Z-Pak, allowing for public health miracles against trachoma.
It's an incredible journey.
And we confronted the harsh reality of antimicrobial stewardship, how our demand for a quick, convenient blister pack is driving bacterial resistance and exposing patients to hidden cardiovascular risks.
Is a profoundly complex legacy for a remarkable class of drugs.
It really is. And I want to leave you, the listener, with a final thought to mull over. It's the great paradox of the Z-Pak, the exact pharmacological trait that makes azithromycin incredibly convenient for you to take.
That 68-hour half-life.
Right, where the pills stop but the drug keeps lingering in your tissues. Well, it's the very same trait that provides a training ground for bacteria to become immune to it. As we move forward into an era of increasingly resistant superbugs, are we ultimately doomed to have to choose between drugs that are highly convenient to take and drugs that actually work long-term? Next time you pop open that cardboard blister pack, maybe give a little thanks to that Philippine dirt and wonder just how much longer its magic will last.